Okay, now I just say, if the collision is elastic, the relative velocity after collision is equal and opposite to the relative velocity before. Now that comes out of conservation of kinetic energy. The sum of the 1/2 mv squareds before has to equal the sum after. You could write that as an equation. And the total momentum before. And you could write total momentum before equal total momentum after, and you use M1 V1 and M2 V2 and M1 V1 after and M2 V2 after. And you could write out those two equations and then do a little bit of pretty tricky algebra and conclude that the relative velocity is opposite after collision to before. But before we can even talk about that, we've got to talk about what relative velocity means. So I say, okay, I'm driving down the road 60 miles an hour. Now somebody else is driving down the road at 70 miles an hour. Okay, what's her relative velocity as I observe it? Well, I observe her going down the road, going by me at 10 miles an hour, don't I? It should be fairly obvious. So if I'm traveling south and south is the positive direction, then she's moving at plus 10 miles an hour relative to me. Now if north is the positive direction, well, she's moving 10 miles an hour past me in that direction. That would be negative 10 miles an hour, right? Relative to the northward direction. So, you know, all these reference frames are relative. I haven't defined what a reference frame is, but I'm going to use the word loosely. So, from her perspective, though, I'm moving backwards with respect to her. So I'm moving, if her direction is positive, then I'm moving at negative 10 meters per second relative to her. Okay? Now if she thinks north is positive, then she's going to say, well, I'm moving at plus 10 meters per second relative to her. In any case, that whole idea of relative motion is really something we experience all the time if we drive and pass cars and cars pass cars. So we can actually think of it, although if you're driving, don't think too hard about that because you don't want yourself to get distracted. You know, you can just kind of see what's going on. You remember what it looks like. So think about it after you're safely out from behind the wheel. Okay, well, where in the world did I write it? Okay. Well, the first thing I just wrote is, because in a collision, because of the impulse momentum, again, the change in momentum of the first object is equal and opposite to the change in momentum of the second. Because, once more, the forces are equal and opposite, so the impulses are equal and opposite. Then I got into a little notational confusion, which I finally reconciled. Yeah, there wasn't anything incorrect about what I was writing down, but it would have been confusing, so that was an error on my part. I'm going to let W1 and W2 be velocities before the collision, U1, U2 the velocities after collision. Now there are various ways of doing this. I could do like a V1B and a V2B and a V1A and a V2A for the velocities V1 and V2 before and after collision. I chose to use these letters, okay? So you got W1 and W2 are the velocities before, U1, U2 the velocities after. Now clearly, implicitly, the subscripts refer to which particle, which ball in this case. Then I say the relative velocity of W2 with respect to W1. Well, again, 70 miles an hour versus 60 miles an hour. From the 60 mile an hour perspective, relative velocity is 10 miles an hour. How do you get that? You take this velocity and subtract this. Okay? So the relative velocity of W2 with respect to W1, that would be our 70 mile an hour with respect to 60 mile an hour, would be W2 minus W1, 70 minus 60. Okay? And then clearly a relative velocity of u2 with respect to u1 would be u2 minus u1. And in an elastic collision, these velocities, these relative velocities are equal and opposite. Okay, so this is equal and opposite this. It's equal to the negative of this relative velocity. This relative velocity is the negative of this. The before collision relative velocity is equal to the negative of the after collision relative velocity. Now this leads us to what? In the current situation, we know the velocities of the two balls before collision. So we know W1 and W2. We don't know U1 and we don't know U2. That's two things we have to find. So we're going to have two unknowns. We're going to need two equations. Hopefully they'll be linear equations. It turns out they are. If we use this property of the relative velocity or this condition for an elastic collision. So we know W1 and W2. And W2 minus W1, well, W2 is 0, up. Yeah. W2 being the velocity, now I lost track, so if you're losing track, well, join the club. Okay, W2 is the velocity of the first object, the second object before collision, that's 0. W1 is the velocity of the first object before collision, that's 4 meters per second, so W2 minus W1, velocity of the second minus the velocity of first before the collision, is 4 meters per second. Then, that's got to be equal to the negative of U2 minus U1, velocity of the second after collision minus the velocity of the first after collision. The two things we don't know. So it follows, well, this is negative 4 meters per second. It's got to be equal to the negative of this, so that U2 minus U1 is going to be plus 4 meters per second, and you can do the algebra. It's very trivial. Okay? So we get U2 has to be U1 plus 4 meters per second. We know also the change in velocity of the first object we don't know that. Delta V1, okay, we're going to use this equation, so we're going to look at delta V1 and delta V2, okay? Delta V1 is the velocity of the first ball after collision minus the velocity of the first ball before collision. The after collision minus before collision velocity. That's what we mean by the change in velocity. What happens after minus what was there before. Okay, so delta V1 is this, and that's going to be U1, that's the velocity of the first ball after collision, minus the 4 meter per second velocity of the first ball before collision. So that's our delta V1. Our delta V2 is U2, which is the velocity of ball 2 after collision, as defined here, minus 0, and of course that is equal to U2. So we have this equation, which becomes M1 times the delta V1, the U1 minus 4 meters per second, and that equals negative of M2 V2, and I think I didn't write my negative. If you're taking notes, I hope you watch this. Okay, so we have negative of the mass of the second object, which is 3/2 m1, times the change in velocity of the second object, which is u2. And then we also have the equation we have here. And now we have two equations which are easily solved for u1 and u2. I mean, this one already tells you, in this case, what u2 is. And if it didn't, in general, it would be u2 plus some quantity. And you could solve for u2. In any case, you get something here that you can plug in for u2, which is u1 plus 4 meters per second, and then you just deal with the linear equation, which is very easy to do. So, what I ask you to do now is solve this and confirm the conservation of kinetic energy.